Faisal, and this webinar is organized by Professional and Educational Activities Subcommittee, IEEE Power and Energy Society Young Professionals. Today, our guest speaker is Dr. Behnam Mohammadi-Ivatloo. Dr. Behnam is professor at the University of Tabriz, Iran. He worked as a senior researcher at Aalborg University, Denmark. He was a research associate at University of Calgary, Canada. He is a senior member of IEEE and a member of the governing board of Iran Energy Association, where he was elected as the president in 2019. He is serving as editor and associate editor for different journals such as IEEE Transactions on Power Systems, IEEE Access, IET Smart Grid, and Sustainability. He is included in 2018, 2019, and 2020 Thomson Reuters list of the top 1% most cited researcher. He is expert in the field of integrated energy systems, renewable energies, microgrid systems, and smart grids. Today he will talk about utility-scale energy storage systems. I would like to welcome Professor Behnam for further discussion on the topic. Please, Dr. Behnam.
Thank you very much, Shah, for inviting me and for organizing this webinar. And also thank you for your kind introduction. Okay, I'm going to share my screen. Can you see my screen as I'm scrolling?
Yeah.
Okay, perfect. Today, we are going to talk about utility-scale energy storage systems, or in other words, about the large energy storage systems. Just to give some introductory and preliminary about the topic, we all know that the unit of energy is joule. We also use a watt for the unit of the power. That is also can be considered as joule per second. And if we use this equation, we can say that 1 watt-hour is equal to 3,600 joule. And in other words, 1 megawatt-hour is equivalent to 3.6 gigajoule. And this is just for this that sometimes the energy capacity of storage systems is presented by gigajoule, sometimes by megawatt hour or watt hour. Then you can use this equivalent equation. Other important preliminary about the energy storage systems is that we should know some information about them. For example, just knowing the energy level of the storage system is not enough. We need to know the energy level, we need to know the power rate, and also by knowing this two information, we can calculate the duration at the nominal power that this storage system can be charged or discharged. Also, after knowing the power of the energy storage system, we should know the voltage level or current level of the storage system. If we know the power level and voltage level, it is obvious that we can calculate the current level of the storage too. And the main point in the energy storage system that we are going to store the energy now and to use it later. This can be done for different objectives and different purpose. We are going to talk about this, the objectives, and why we are going to save energy now and use it later. And we know that this can be done using some energy storage medium. Also today we are going to talk about the different mediums for energy storage. Then this slide just provides an overview of the applications of energy storage systems. It can be used for renewable energy sources integration. We will talk about it. It can be used for price arbitrage. Just you can use energy storage to buy energy at low prices and sell it at high prices and gain revenue by this arbitrage. It can be used as ancillary services for providing ancillary service for balancing the frequency of the system and other ancillary services in the power system. It is obvious that it can be used for peak shaving by discharging the energy storage at peak time and charging it at off-peak time. We can use it for peak shaving in the system. And also, it can add a flexibility for the system by providing different services like as ramp up and ramp down services to the system. And also, it can be used in system to maintain the electricity price in a rational level to avoid from high price spikes. Here is one of the questions that why we need energy storage for renewable energy system integration. This slide shows that the output of wind farm, and this diagram is for 2 weeks. Each of them here you can see for 1 day. You can see that the output of the wind farm is totally different in different days. It means that you can see for some days we have almost zero generation, but at other days we almost have the generation at the nominal power. Then we cannot rely on this type of the generation systems in the system, and we need some other medium, some other supports to use effectively in the power systems. Here is another diagram showing the daily variations of a wind farm during a month. Each of these curves with different colors is related to 1 day, one specific day in a month. And you can see that almost all of the this area from minimum to maximum power is covered by the generation in different days and different hours of the day. Here is another figure that is well-known diagram in power system operation. It is used for different purposes. It is for CAISO, for California ISO. It shows that the net load in different years. You can see that then we should first define the net load. Net load means the actual load of the system minus the generation of renewable energy systems. Then the net load should be supplied by conventional generation systems. Conventional generation system, I mean the generation system other than renewable energy systems. Then here you can see that year by year, by increasing the renewable generation, you can see that the net load is going to be similar to duck curve. And this curve is also known as duck curve. But the important point about this curve is the change in short time. That we call it ramp. Here you can see that, for example, in this system, we need about 13,000 megawatt ramp that should be provided in 3 hours. It is ramp up, and also we have ramp down. Then, if we are going to provide these ramps with a conventional generation system, we need to have a lot of spinning reserve provided by conventional generators. Another measure could be the energy storage system. Here is the study of the same curve with the energy storage system. The blue one shows that what happens if we are using energy storage system. And we can see that by using a proper energy storage system, about 60% of their peak ramp can be reduced. Here is the summary of the energy storage allocation applications in different allocations. It means that in front of the meter and behind the meter. For in front of the meter or for utility side applications, we can talk about the bulk energy services like as arbitrage, electric supply, capacity, and peak shaving. For ancillary services, we can name frequency regulation, voltage support, black start, spinning reserve, non-spinning reserve, and load playing and load balancing as the applications of the energy storage for ancillary services. For grid support services, we can name transmission service, upgrade deferral, and congestion relief. The same can be applied for distribution services and also can be used for peaker replacement. Also, it can be used for renewable energy integration, for time shift of renewable energy, for capacity firming of renewable energy, and also for grid integration. Energy storage system can be used in the customer side or end user scale behind the meter application. Different applications we can name for this, like as power quality and reliability. It can be used for increasing the power quality of the customer, or it can be used for bill management of the customer. It can be used for demand shifting, for peak shaving, and also now it can be used to increase the generated self PV to consume the generated PV. And also it can be used in standalone or islanded systems. Here is an overview of the installed. In the left-hand side, you can see the installed energy storage capacity. You can see from 2013 to 2018, has an exponential growth. And also, in the right-hand side, you can see the estimation for the next years. And the main important point about them that for the past and for the future, you can see we are observing an exponential growth in the energy storage applications. Here, just some examples for different states in USA. These are here just to show that in utility level, in state level, in country level, and in global level, we have a great tendency to use more and more energy storage system. And you can see that all of the states have specific plans to increase the energy storage, and they have different targets for energy storage application. Here, we are going to talk about the mediums for energy storage or different energy storage technologies. It can be divided to different types like as mechanical, electric, thermal, chemical, and electrochemical. And in each category, you can see different types. For example, in mechanical, you can see pumped storage. We will talk about it. You can see flywheel, compressed air. We also discussed this type of energy storage system in this presentation. Or capacitor and SMS can be considered electric storage systems. We have a thermal storage system. It can be type of molten salts or chillers. We also have chemical storage systems like as hydrogen and methane storage system. And in the last category, we have electrochemical one that is divided to conventional batteries, high temperature batteries, and flow batteries. For the grid scale energy storage systems, we have different types like as pumped hydro storage, compressed air energy storage, thermal energy storage, supercapacitor and flywheels, battery storage systems, and power to gas storage. We are going to talk a bit more about this type of storage systems. Here you can see the share of different energy storage systems. This is for the USA, but the same thing happens in the world. It means that more than 90% here in USA, for it is 94%. For the world, we also have this value and about a bit more than this one. Most of the energy storage system in the USA and in the world is pumped hydro. We can say more than 90% of energy storage system. And the remaining one is divided between thermal storage, battery, compressed air, flywheel, and other type of storage. I assume that pumped storage system is one of the well-known storage system that is known for everyone. Here, for the pumped storage system, we have two different reservoirs. One is upper reservoir, and the second is lower reservoir. Here you can see the in the real world application, upper reservoir and lower reservoir. And based on our need, when we are at peak time and we are going to generate power, the water flows from the upper reservoir to the lower one and generate the power. And in the off-peak time, we are pumping the water from lower reservoir to the upper reservoir, and this set is operated as a load, as a demand for the power system. You can see that this technology is a mature technology. Its cost is, we can see that it's low in comparing with most of the storage technologies. And it has a very good response time. It can be in operation in seconds to minutes. And it also has a acceptable efficiency that is more than 80%. And just note that for energy storage systems, we have two cost terms. One term is for the power, here you can see, and also one term for the energy. Here, it's just a screenshot of the Excel file that you can find it in the website of the US Department of Energy. In that file, all of the energy storage projects around the world are collected, and the main characteristics are provided. Here I just filtered the type by pumped hydro storage to see the different hydro storage systems. And you can see that we have a different type of energy storage here, and status for them announced. It's going to be the largest pumped hydro storage, and it will be in Canada, and the size is 4,000 megawatt. The operational one, the largest in operation one, is 3,003 megawatt, and the unit here is a kilowatt for these numbers. Recently, we have different pumped hydro storage projects. Here, just for examples, we have provided the information for some of them. You can see in different countries, we have a larger scale pumped hydro storage systems, and you can see the capacities are indeed very high, from 200 to 1.2, 200 megawatt to 1.2 gigawatt, and also you can see that it's around the world. Other type of the energy storage system that now they are popular in utility scale too is battery storage. Battery storage systems generally used as a small scale storage system, but now we have a package of the battery storage system that are large enough to be used in utility scale. We will discuss a bit more about them. And for the battery storage system, here in the side, you see the share of the different battery storage technologies in the installed battery storage technologies. And you can see that year by year, the share of the lithium-ion batteries is increased, and it is the dominant type in the world now for the battery storage systems. And this is a forecast for the future price of the battery storage system. And you can see that all of the forecasts show that the price of the battery will be reduced. And here you can see that, for example, some works have forecasted that the price will be about 20% of the current price, and the highest one here. And if we consider the midest one, the medium of this forecast, we can say that by 2050, the price for the battery storage systems will be reduced at about 60%, and it will be about 40% of the current price. Here is an example of the utility scale application of battery storage system. This project is in Japan. Here you can see that there are wind turbines. The wind turbines are 34 wind turbines with the capacity of 1.5 megawatt. And also here we have the battery storage system. The type of the battery is sodium sulfur, or NAS, or we call it NAS battery. And you can see that the size of the power rating of the batteries are 34 megawatt, and they can store 245 megawatt hour of energy. That is a quite large amount of the energy. And in the left-hand side in the table, you can see the information of this project. You can see that it is started in 2000. Total capacity is 85 megawatt, in which 51 is for wind and 34 for the battery storage. The efficiency of this storage types is very good. It's about 90%. And here you can see other projects in the world for the sodium sulfur batteries in different countries. Here you can see that, for example, in UAE, we have a battery, a NAS battery with the size of 40 megawatt that is used for load leveling. And also in other countries, you can see that it is used for different application. Here is the recent projects for battery. Recently, large battery storage projects announced in different parts of the world. You can see we have quite large battery storage systems projects in 2020 and 2021. And they are based on the lithium-ion battery. As we discussed, that is the dominant one and the most used one in recent years. Other type of the large scale energy storage system is the compressed air energy storage. In this storage, we are using the power from the grid in off-peak times to compress the air, and the compressed air is injected to the cavern, in underground caverns mostly. This is for the case. And in the peak time, we are that is stored in the cavern to produce the energy. And here you can see that it is the high pressure turbine and low pressure turbine here is similar to one that we are seeing in gas powered power plants. And we have two of them that is in operation for more than 20 years, one in Germany and one in USA. In Germany, we have the compressed air energy storage system with the size of 320 megawatt, and in USA with the size of 110 megawatt. There are two types of the compressed air energy storage system, as you can see here. The first one is diabatic one. In the diabatic compressed air energy storage system, you can see in the discharging process, in the process that I am going to generate the power from the compressed air, I need natural gas input to generate the power. The difference of the adiabatic with diabatic one in this part. In the adiabatic one, you can see that when charging the storage, I am storing the generated heat in the thermal storage, and when I'm going to discharge the system and to generate the power, I'm using the stored heat here. Then for the adiabatic compressed air energy system in the generation phase, you are not required to supply external fuel to the system. Here you can see that it is just an screenshot of the company that is showing that they have running about 2 gigawatt of energy storage systems. It is just to show that this type of storage system will be common in next years. The compressed air energy storage systems are highly reliable, and they have a long lifetime. They are cost effective. Also, they have a low environmental impact. Indeed, you can use them in the places that they are salt cavern and use underground or abandoned systems to store the compressed air. It also has a high power rating, and it's an efficient one, and also the response to the load change is high. Here are examples of some recent projects about case or compressed air energy storage, you can see that there are different projects in recent years with different size from about 2 megawatt to 125 megawatt, and it will be in different parts of the world, in Canada, in USA, China, Australia, and also USA. And the next type of the storage is thermal energy storage systems. In the thermal energy storage, we have also different technology for them. Here also you can see that in recent years, different thermal storage systems started and commissioned in the world. And the largest one is going to be in Morocco. It will be accompanied by the world's largest concentrated solar power plant with molten salt storage. The other type of the larger scale storage systems is power to gas storage. In this type of the storage, we are using the mostly renewable generated power to electrolyze the water. Then we can, here you can see the water as input, and also other input, the electric power. In the electrolysis process, the output will be hydrogen and oxygen. This hydrogen can be used directly or can be injected to the methanization process. In the methanization process, we can combine the hydrogen, and we also use CO2. That is a harmful gas to the environment. We can use this technology as a carbon capture technology too. And you can see that in the methanization process, the output will be methane. Methane is the gas that is used in natural gas network. Then the output can be directly injected to the natural gas system. Then also in conventional turbines, gas turbines, it can be reconverted to the power and injected to electricity. The main point that here you can also inject the hydrogen directly to the gas network. But if you are going to directly inject the hydrogen to the gas network, there is a limitation on it. Based on the different networks, some numbers between 1% to 7% is considered as the safe percent of the direct injection of the hydrogen to the natural gas network. But if we use methanization process, then there is no limitation, and we can inject the generated methane to the natural gas network. This technology is not too mature now, and also the efficiency is low. The efficiency of the system, if we consider the power-to-power efficiency, it means that we calculate the efficiency for the full cycle. But it's going to be one of the interesting storage systems, because it can connect different energy carriers, power and gas, and for this it is more focused in the recent years. Also, this technology has the highest energy storage density, and also can be used for effective energy transportation, and also can be used in systems that we have limitation on power system, but we have some reliefs in the natural gas infrastructure. Then it can be used in these systems too. it can be used for long time storage system, and by increasing the efficiency of the electrolyzer system in recent years, we expect that this efficiency will be higher and higher in upcoming years, and this technology will be one of the common technologies. Here is the efficiency for different power to gas pathways. If we consider the power to power, the efficiency will be very high, you can see. Then if you are going to use power to power, power to gas storage systems, then it can be economical in the cases that you have extra renewable power generation, then or you have renewable power spillage. In this type of systems, power to gas can be economical. Otherwise, by considering that this low efficiency, it may not be economical. But we may consider that other pathways for the power to gas systems, for example, power to methane or power to natural gas, and also here you can see that, for example, for power to hydrogen, if we consider the scenarios for the future emission-free transportations, hydrogen is one of the prominent. And then if we consider the power to hydrogen, we can see that the efficiency will be much higher. Here are the some recent projects that announced in recent years. In different countries, you can see that there are some demo types, or some of them are real and utility size P2G projects. For example, in the France, we have two large projects that will be in operation in upcoming years. Here, we are going to talk about the flywheels. Flywheels, here you can see how they work. In flywheels, we have a big mass that is a rotating mass, and in the charging mode, we can use the energy sources, and in this electric machine in the charging mode will be acted as a motor, and will cause that this will drive this mass to rotate. Then here we have a clutch. Here we can see the clutch is engaged. Then when we are going to store the energy, this clutch will be disengaged, and here you can see that this rotating mass will continue to rotate. We also know that there is a friction, and there will be some losses here. In the discharging mode, when we are going to recover the stored energy in this rotating mass, we engage the clutch, and this machine here is acted as a generator. Then the energy of this rotating mass can be converted to the electricity. We know that as the speed is not constant here, we may need some inverters after the generator too. But note that the amount of the energy here is very limited, and the flywheels power rating is very, very high in some cases, but the duration of the power delivery is very, very short. For example, here you can see two flywheel projects. One is in Institute of Plasma Physics in Prague. And the last one here in the last row, you can see the other one. It is also in Max Planck Institute of Plasma Physics. Here you can see that the power rating is, for example, for this case, is 387 megawatt, and but the duration is only 12 seconds. Then here you can see for the first one is about 5 seconds for the rating of 70 megawatt. Indeed, this type of the storage is used when we need high power for short period of the time. You know, if I'm going to, for example, for the Max Planck Institute, if I'm going to provide this power from the grid support, it means that about a city, that this power rating is the one that we need for a medium-sized cities. But for example, in plasma physics for fusion processes, we just need it for some short periods, say for 10 seconds. It's a pulsed power system. Then here they are using flywheel. The motor size here, for example, in the Max Planck Institute is about 15 megawatt. Then this flywheel is charged by this motor to rotate. For example, in 15 minutes, in 10 minutes for some minutes, and after a while, when it is reached the nominal speed, then you can use the flywheel to discharge it in higher power. Here you can see some recent works from our lab that are related to the large-scale energy storage systems. In this work, here you can see the title of the work and the journal name. If you are interested, you can have a look. And if you have any question, I will be happy to answer it. Here, a multi-objective optimization is used to study the power-to-gas technology in co-optimization of power and gas networks. In the second work, we have studied the power-to-gas technologies in the network constraint unit commitment, but it is a multi-carrier network constraint. Indeed, we have network constraint unit commitment as shown in the left-hand side. But when we have a multi-carrier network constraint unit commitment, we need to consider the power network, gas network, and the district heating network constraints, and to run the unit commitment in this medium. Another one that we have used compressed air energy storage technology in them is in virtual energy hubs. In this work, we propose the concept of virtual energy hub and presented strategies for its participation in the different energy markets. Here we considered electricity network and thermal network. In the other works, we have considered transportable storage, large battery storage that can be transported using a terrain network. And in this study, we considered the constraint of the electric network and also rail transportation network. And we have studied in from two objectives: operational cost minimization and also emission minimization. I would like to thank for your attention, and also I would like to thank Mr. Alirza Akbari Dibabar and Mohammad Mirzai, our lab members, helping in sharing these slides. I'm here if you have any questions, and also my contact email is here. I will be happy if you have any question to answer it, if I can, by email too. Thank you all again.
Thank you, Professor. It was really very interesting topic, and we learned a lot. So I'm looking for question. If there is any question, you can ask here. You can type it the question, and I will repeat your questions. Anyone have question? Please type your questions here. So I have my question about power to gas. Like P2G is expensive, as the electrolyzer are expensive, and economically it is expected that in 2040 or in 2030 it will be like cheap and economical for the consumers. So the deficiency is that when we are converting power to gas, so the efficiency is decreasing further. So
Yes.
how can we select like the electrolyzer like PM electrolyzer, or is the alkaline electrolyzer is the old technology and most of them are now using the proton exchange membrane electrolyzer. So can you tell something about this?
Yes, indeed, we consider electrical energy as a high-level energy. In in converting power to gas, we are going the reverse path. We are converting the high-level energy to low-level one. But the important point that is that, as you mentioned, it is not so efficient now. Now we can use in the places that we have a cheap power. We have low cost power. And this can happen in the systems that they have a lot of renewable energy generation. For example, in Germany, we have wind power splage. For this type of the systems that we have extra renewable energy generation in some hours in the year, and this type of the storage can be useful because you have very, very low cost input. Then efficiency here is not so important for you. You can use it well. If you are not going to use it, it will be just lost.
Yeah.
This is for the first part of the question. Then by increasing the renewable energy penetration in different systems, we can expect that, it's going to be economical to use power to gas, even with these very, very low efficiencies, about 20 to 30%. And about the technologies of the electrolyzers, indeed, we have some pioneering ones like as alkaline and PM, but for the specific project, we need to study that which type of the electrolyzer is good for that project, because it depends on a lot of the parameters and characteristics of the system.
Yes. Thank you.
You are welcome.
Anyone have question? They can type your question here. Okay, I have one another question related to fuel cell.
Yes.
Like when we are converting power to gas, and we can also directly connect the hydrogen, inject the hydrogen to the fuel cell.
Yes,
So
yes, indeed. Yeah.
yeah,
Thank you for mentioning this pass. Yeah, it is another the passes to complete the power to gas cycle. We can use the hydrogen. Indeed, for this type of the application, we need hydrogen storage, and using the fuel cell, we can convert the stored hydrogen to the power. This is also more efficient than the path that we are going to convert power to methane and convert methane to the power. But the main challenge is here about the large-scale hydrogen storage systems. We have a different challenge, different safety challenge also for large-scale hydrogen storage technologies. They are not so mature now, but also it is a hot topic for the colleagues in chemical engineering departments and
Yeah.
related departments. Yeah, and it could be a very good option if we have economical hydrogen storage systems.
Thank you very much.
You are welcome.
There's a question from audience that converting extra power to hydrogen is not dangerous.
The converting, no, it's not dangerous, but we may have some safety concerns about the uh, transferring and transporting hydrogen. For this, in most of the cases, they are saying that, okay, I'm going to convert the hydrogen on site to the methane. Uh, but also, we all know that hydrogen economy is going to be one of the dominant ones in the future. And we will have a very, very reliable methods, reliable devices to transport hydrogen to. As you know that already we have uh, hydrogen-based cars in the market, in the industry now.
Yes. I have one more question. Like when we are uh, like planning for a P2G system, and we are we have a surplus electricity. Let's suppose we have 1 megawatt, and we are converting it to gas, hydrogen. So how can we select the electrolyzer for this, like the capacity of electrolyzer?
Yes, it is similar to that the work that we are going to do for energy storage allocation
Yeah.
in
Yes.
in generic term. For energy storage allocation, we are looking at what's the conditions of the system. We getting the, for example, load profile, the generation profiles for different hours of the year, and also the different expansion planning for network parts, for the generation parts, and also load growth. And based on that, we are running an optimization method and to select the storage size and storage location. The same is done for the electrolyzer. I know that I'm aware that, for example, there is an European Research Council supported project for the uh, distributed electrolyzer sizing and location. Then this is not a question that I can answer that, okay, for this type of the system, you can use uh, this size of the electrolyzer. Then we should have a perfect picture of the system that we are going to implement electrolyzer there. And based on it, we can run an optimization problem and obtain the optimum size of the electrolyzer. Even we can uh, change our optimization and to show our the most beneficial electrolyzer technology too. You can also formulate it and to see that which type of the electrolyzer will be uh, good for your project.
Thank you very much.
You are welcome.
Anyone have question, they can type it here. And if we are Like what you want to say about like steam power plant and power to gas system?
How to relate them?
Yeah, how to
Um,
relate them?
uh, in that they are a bit different. If the
Yes.
it could just we can relate that if it's a gas-powered thermal plant,
Yeah.
then here, okay, we can say that using power to gas technology, we are going to generate the methane, and this methane can be used in the gas-powered thermal power plant to produce the electricity. As I mentioned, this is not a efficient way unless that your input power be a free power or very, very cheap power.
Yeah. That's like we are considering renewable energies for that.
Exactly.
Okay, there are some questions I will. The question is which optimization or machine learning methods are commonly used for choosing optimal storage?
Uh, Perfect. Indeed, this type of the uh, problems, mainly at the end, you will have a mixed integer nonlinear programming problem because we have some decision variables to determine the location of the storage systems. Then we have binary or discrete decision variables. Also, we have some continuous decision variables. And if we consider the network constraints, for example, you should consider the power flow equations and other equations in the system to see that what will be the impact on voltage of the system, on the power flow of the system. Then it will be converted mixed integer nonlinear programming. For MINLP, we can use the mathematical optimization methods that are developed using different solvers that you can find in Python or GAMS. It could be one option. If you well define your problem, I can recommend it. Otherwise, because this is a MINLP problem and we don't have a method that guarantee the optimal solution, the global optimal solution, you can use artificial intelligence-based algorithms or meta-heuristic algorithms, and you should look at your problem and see that which of them is better for your problem, and you can get better results with them. It is hard to say that for mainly for the artificial intelligence-based optimization algorithms, it is hard to say that which one is better because they are acting with different performance for different problems. And you should just test it and to see that if it's going to be a good choice for your problem or not.
Right. Okay, here are some questions. Uh, Question about using learning-based methods like neural networks based model predictive control future in the field of increasing energy efficiency.
Yeah, for example, MPC or uh, neural network-based models and algorithms like as, for example, reinforcement learning techniques can be used generally for the operation of the storage systems. And you can see different papers that studying, for example, uh, application of energy storage for frequency control. You can see that they have used different neural network-based methods or also different control techniques like as MPC. For this type of the control methods can be used in real-time operation of the energy storage system and the short-term operation of the storage system. For the long-term operation or for long-term planning, be mainly using the optimization algorithm that is discussed in previous question.
There's another question. What's your opinion about using quantum-based methods such as quantum neural networks uh, for demand response prediction with less execution time and its contribution with energy storage?
You know, we should look at what will be the added value of this technique. And if this added value is important for me, for my customer or not. For the defined scenario, I suppose that no, it is not a good option because for the defined problem, we are not in rush. We have enough time to decide and to act. But sometimes we are working on real time, and for these problems, the control time and your decision time is very, very important. Then, yeah, this type of the accelerated algorithm that can solve the problem in shortest time will be prepared. But for the demand response forecasting for energy storage, for example, operation, in general, they have, I can't see much added value to have a method that is very, very fast.
Okay, thank you very much.
You
Okay,
are
I'm
welcome.
reading the questions, but there are no more questions from here. If someone is asking, so they can type it, but no more questions here. All right. Okay. Thank you, Professor. And thank you, everyone, for joining us. Professor, it was really very nice session. And we learned a lot from you. The topic was very interesting. And I really I'm very thankful to you for giving us the time. And thank you, everyone, for joining us and asking the questions. Thank you very much, Professor Behnam, for your time and sharing your knowledge with us. Hope to see you in future. Thank you very
Thank you
much.
very much for your invitation. I appreciate your time, and also I appreciate the audience to joining this webinar. Hope to see you next time in person.
Sure. Thank you very much. Bye.
Have a good time. Bye.
Bye.